Today we're going to handle a little bit of the mathematics behind waves. Some of the things that we do measure are frequency and periods. The frequency of a wave is the number of wavelengths that pass a fixed point each second. For example, in the electromagnetic wave notes we saw yesterday, gamma rays have a much higher frequency than do radio waves. And so that's what we're talking about with frequency. You can find the frequency of a transverse wave by counting the number of crests or troughs that pass a point each second. Frequency is expressed in the unit hertz. Hz is how that's abbreviated. And it is actually the unit per seconds, not seconds, but per second. So the seconds is in the denominator. Or we can write it like this, 2 per seconds, or s to the negative 1, because you know a negative exponent means you can put it in the denominator and make it positive. The period of a wave is the amount of time it takes one wavelength to pass a point. So as the frequency of the wave increases, the period decreases. Period has a unit of seconds. So basically, period is the inverse of frequency. That's how they're related. Let's take a look at the two that we will be discussing the most and have your homework assignment, and that's frequency and wavelength. As frequency increases, wavelength decreases. That means they are inversely proportional. That means if you multiply them together, they will equal a constant. And so if you take frequency times wavelength, you'll end up getting the speed of the wave, and that is the wave speed equation. And so the frequency of a wave is always equal to the rate of vibration of the source that creates it. If you move a rope up and down and back in 1 second, the frequency you generated was just 1 hertz. So 1 wave per 1 second is 1 hertz. You can calculate the speed of a wave represented by the velocity by multiplying it. And so this will be the equation we will be using. And you can see that you have 3 variables. So that means we can do one of our magic triangles, which I've done for you here. And so wavelength is in meters, frequency in hertz, and speed in meters per second. And let's take a look and tackle some sample problems. What is the speed of a sound wave that has a wavelength? So this is the wavelength value. Notice the unit meters. And a frequency of 175 hertz. So what I'm going to do is I'm going to multiply these two together, and I'm going to end up with meters per second as my unit. And so I'm going to take, I'm using speed equal frequency times wavelength, V equal F times lambda. And so I'm going to take 2 times 170.5. And I'm going to put that on my calculator. So 2 times 170.5 gives me 341 meters per second as my final answer. The second example is actually asking the same thing. It's asking me to find the speed of the wave. So I'm going to do the same thing. I'm going to use the formula. Velocity is equal to frequency times wavelength. So I am going to take 6 meters times 250 hertz. Instead of saying hertz, what if I wrote it per second? So then maybe you'll see how I'm getting meters per second as my unit. So I'm taking 6 times 250, and that gives you 1,500 meters per second. And so we found the speed of that wave. Now this time I'm asked to find the wavelength. Anytime you're asked to find wavelength or frequency, you're going to have speed in the numerator and the other one in the denominator. So here's my speed. So that's going to be my numerator. Here's my frequency. Wavelength is equal to speed divided by frequency. And so I am going to take my wave speed of 340 meters per second, and I'm going to divide it. Instead of writing hertz, I'm going to write them as per second. So you can see how that cancels, and you get the units of meters. So I'm going to take 340 divided by 20, and that will give me 17 meters. So it's probably a radio wave of some kind. And so that's your wave problems. I do want to go on and talk a little bit about amplitude. Amplitude is the amount of disturbance from a wave. It's actually the height of the wave. And so when you plug in an amplifier to a musical instrument, it doesn't change the wavelength or the frequency. So here is, maybe a regular sound wave coming off. I know I'm showing it as a transverse wave because it's just a little bit easier. And then if you plug in an amplifier, you have to match the same wavelength, just increasing the amplitude on it, or you're not going to have the same sound. And it's going to sound more like noise than music if you don't have a good amplifier. The greater the wave's amplitude, the greater the disturbance the wave produces. Amplitude is measured differently for longitudinal and transverse waves. You just saw me show you a transverse wave. It is the height of the wave. And then for a longitudinal wave, it's how tightly the medium is pushed together at the compression. So, if it's, this would be less amplified, and then this would be highly amplified. And so you see that it's more compressed. And so the denser the medium is at the compression, the larger the wave's amplitude is, and the more disturbance the wave creates. So again, here's a picture of a longitudinal wave, and here's the transverse wave. And if I want change to a higher amplitude, I am going to increase the height of the wave or increase the number of compressions. This one has a higher amplitude than this one does, is our example. So if a wave has a high point and a low point, is it a longitudinal or transverse wave? Well, when you're talking high-low, you're going to be talking about a transverse wave. What is the wavelength of the wave? It is measured either crest to crest, trough to trough. Any two like periods on a single wave is what you're measuring. And so the third question, which of the following refers to the number of wavelengths that pass a fixed point each second? That is its frequency, and it's measured in hertz or per seconds.